Check one. Check one. Check one. A very good afternoon to all of you present here at the computing session. First of all, I would like to apologize to Dr. Barbara Villani. We have been keeping you waiting for a very long time now, and we're really sorry about that. Without wasting any more time, let's get into the real deal. Starting off with the invited speech by Dr. Barbara Villani from the University of Westminster, United Kingdom.
Hello, can you hear me?
Yes, ma'am.
Okay, hi.
Hello.
Hi. So if it's okay, I can share my screen and I can start the presentation. Okay, can you see my, okay, great. Hi everybody, good morning. My name is Barbara Villarini. I'm from the University of Westminster, and today I'm going to talk about artificial intelligence for automatic organ reconstruction and morphological feature extraction from medical images. And we will see which is the impact on healthcare. So, regarding the outline of this speech, I would like first give you some information about my background. We will see some research projects I was working on, particularly focusing on the aim, the objectives, which are the challenges and the contributions. We speak about the methodology that we are using in order to achieve all these goals and current results and achievements. I would like also then to speak about future works and current works that we are actually starting to work on till drawing the conclusion. So this is me. I received my PhD in information engineering from the University of Perugia in Italy. I was working mainly on image and video processing, developing objective quality assessment and error protection algorithms for images and video. Towards the end of my PhD and for other years, I have been working also as a software engineering and researcher in one of the research company in Italy, focusing on innovative digital cinema application until 2013, when I moved in London. and I started to work as research associate at University College London. And here, for the first time, I use my expertise and my skill in to solve some medical problems. So I apply my skill in the medical field, and I've been working in one of the research center, the Center of Medical Imaging Computing, developing some application for the non-invasive treatment and biopsy of prostate cancer. Then around 2015, I get an academic position at the University of Westminster. And a couple of years ago, I received the Royal Academy of Engineering Research Fellowship. And during this period, especially during the fellowship that I had, a lot of the opportunity to delve in the medical field, applying what I learned also from my postdoc position in the medical field in order to solve some challenging problems that I'm going to speak now in the next slides. So just to make an introduction of which is the problem that I would like to solve and would like to work on. In the last decades, medical imaging technologies has really revolutionized healthcare. You know that now we have detailed images of the anatomy of the human body, and the number of patients that undergo MRI, CT scan is incredibly high. You need to think that we acquired millions of abdominal images in the UK every year. However, most of the information that could be derived from a careful analysis of such large data set is neglected, mainly due to the fact that the available tools require interaction from radiologists and radiographer who should analyze very carefully each slide in order to identify a specific pattern in the images that could indicate an early sign of specific disease. But of course, this required a lot of effort, a lot of time. Imagine that someone needs to go through all these slides. And when you undergo an MRI scan, I'm thinking that you have to think that an MRI scan has hundreds of images. So this work from a point of view of a person is quite difficult. It's not really feasible. So that's why we are using computational methods. Computational methods are able to analyze automatically a large medical data set. So in this way, we are able to provide unique opportunities to answer clinical and scientific questions, and would commence what we call a subject stratification according the organ morphology. So in this case, we can have chance to make studies in order to improve the analysis and the detection of disease and providing guidance for treatment planning. Of course, there are serious challenges in developing a robust automatic segmentation techniques. First of all, we have to deal with anatomical structures, and some of the organs have high structural variability in terms of size, in terms of structure, in terms of location of the organ. So if we consider here as example the pancreas is this yellow, light yellow organs here. It has a high structural variability among different persons. Also, the location within the abdominal cavity shifts from patient to patient. Furthermore, it lies behind the stomach and often overlaps with surrounding fat vessels. Thus, it's quite hard to identify this organ through a full inspection. Another important challenge is related to different medical image modalities. Patients undergo medical scan based on different acquisition principles. You can think to CT scans, MRI, ultrasound. So we are dealing with different sequences. You can see here in these three images, three different acquisition of the abdominal organs. We have a CT scan and two MRIs, which are acquired from different scanners. So you can notice that the MRI present additional age-based artifacts compared to the CT imaging. This is due to lower resolution and slower imaging speed. And furthermore, within the same medical modality, so I'm referring to MRI A and MRI B, we can see that there could be some differences due to the different scanners, different machine that we are using during the acquisition. And also, we may also have the presence of artifacts due to patient movements. So the task becomes to be quite challenging. A third important limitation, which is important to mention, is that there are some challenges due to the dataset limitations. So first of all, it's quite hard to have a very high number of images manually annotated that could be used to train the artificial networks, to train the AI system. You know that a low number of images during training can lead to low accuracy and high difficulty to test the model. So we need also to take into account this fact. So considering all these challenges, the contribution of the work should be develop a novel and robust automatic deep learning approach, so an AI approach for the automated organ muscle segmentation in volumes of medical images from different modalities. This approach is going to use, instead of 2D features learning, 3D volumetric information, so 3D features. We aim to have a framework which is modular, scalable, and generalizable in order to be used also for other applications. And in order to do so, we aim to evaluate the approach using different datasets, such as MRI, DCMRI. DCMRI is a digital contrast enhancement MRI, where a contrast agent is injected into the patient. And then we target distinct abdominal organs, for example, pancreas, liver, kidneys, and muscles, such as the iliopsoas muscles. And of course, in order to assess, we compare with state-of-the-art in order to also demonstrate the high statistical stability, given the difference in image quality among all these different modalities. And finally, our contribution to the scientific and medical community is to provide a web-based application to perform the automatic segmentation of organs, a web-based application that could be accessible and open source in order to foster collaboration and integration across different disciplines. So these slides shows at high level the proposed segmentation framework. So the idea is that from a radiological scan, we can obtain some prognostic biomarkers, which can be used to predict a condition or its progression. So the initial input is a 3D medical volume, as you can see, that goes through a segmentation process in order to get a 3D accurate reconstruction of the organ of interest. In this case, in this slide, you can see the pancreas. And the segmentation result is then processed through a biomedical model, which compute then all the morphological features for the final prediction of a condition or for the evaluation of its progression. But how do we automatically recognize the organ of interest within the medical image? So we are using deep learning approach. In this slide, I would like to provide the main concept. So we see that a deep learning network is trained using multiple image volumes and respective annotated ground truth of the organ of interest, in this case, the pancreas. So someone, a radiologist or radiographer, annotated manually the organ of interest. So the aim of the training process is to optimize the deep learning network in order to recognize distinguished features and boundaries of the pancreas. And the network is optimized by iteratively minimizing the error between the output prediction and the actual desired outcome, which is the ground truth. And we do so using a loss function through a technique that is called back propagation, which updates the convolutional layers filter, minimizing the overall loss. So when then we go at the testing stage, an image volume, an unseen, so it's this image volume is something that we didn't use during the training, obviously during the training process. So this image volume is processed through the fully trained deep learning network, which performs a pixel-wise or voxel-wise prediction in order to generate the output as a sequence of 2D slice or 3D volume differentiated by pancreas and not pancreas labels. Now, if we want to delve a little bit more in detail, as you can see from this figure, the training stage simultaneously develops a network for localizing the organ of interest and the segmentation network to predict the labels that correspond to organ and not organ tissue. So if now we look at the localization stage, so we are looking at this first part, we downsample our volume and we feed it to a deep network that we call 3dBr unit. So this architecture builds upon a popular network used as a baseline for many medical segmentation tasks, which is called a UNET. So the UNET architecture consists of three main sections. We have the downsampling, which is also called encoder. We have the upsampling, which is also decoder, and we have a bottleneck, which is the bridge between the two sections. And every light blue block that you see in the figure represents a multi-channel feature map. All the white blocks represent the copied feature maps, and then the arrows represent the typical different operation in a neural network. So in the upsampling part, we have a large number of feature channels which allow the network to propagate context information to higher resolution layers. And building on the UNET architecture, we add residual learning blocks, which are using skip connection in order to have an original input added to the output of the convolutional block. And doing so, what we aim to do is to increase the number of connections within the segmentation network, improving the segmentation accuracy and optimizing the process, achieving a faster convergence. Now, this is about the localization. So if I go back, is this part of the diagram of this figure. The second part of the training stage develops a 3D tiramisu model using a uniformly cropped region where the organ of interest is fully present. So now, if we want to see the tiramisu network. So the tiramisu network, you can see the diagram in this image, extends the dense net architecture, which is particularly suitable for the semantic segmentation to work as fully convolutional networks by adding an upsampling path to recover the full input resolution. So we can note that in this case, the upsampling and the downsampling path are different. In the downsampling, the input to a dense block is concatenated with its output, leading to a linear growth of feature maps, whereas in the upsampling, we don't have this. And this approach allows to build a very deep, fully convolutional dense net without what is called feature map explosion. Now, I don't go too much in detail about the architecture. We have some papers where you can have a look to the details, and also all the code is open source and fully accessible. So for the testing, we are using unseen image volume. So for the testing phase, the fully trained 3DB unit performs a coarse segmentation of the target organs in order to find the bounding box to crop the volume containing the region of interest, and then the cropped volume will be the input for the 3D tiramisu model, which performs a fine and detailed voxel-wise prediction of organs and not organs. So we use a high amount of data for different organs and modality. We collected this data and we manually annotated through the help of expert radiologist and radiographer. So we can access to the following data set. As you can see, we have 6 different data sets of MRI, DC, MRI, and CT modalities, targeting different abdominal structures, such as the pancreas, liver, kidneys, and iliopsoas muscle. So in terms of what we get, in terms of result and evaluation, we consider the DSC, the dye similarity score, and the Jacquard index are metrics that represent an accuracy score of the overlapping between the segmentation and the ground truth. Now, in these slides, I provided the segmentation for the pancreas. As I said before, the automatic pancreas segmentation is an extremely challenging task due to the high structural variability of this organ and the similar grayscale intensity of nearby tissue. And the results are reported for 2 different MRI datasets where the data acquisition was made from 2 different scanners, and also 1 CT dataset, which is publicly available. So in the image, the segmentation outcome in green overlaps the ground truth in red, and with the corresponding dye similarity scores. And the results, as you can see, are compared with the state-of-the-art work using the same dataset, and what we obtain with the 3D proposed method outperform state-of-the-art, achieving a high dye score. And also what we are looking for is to have a low standard deviation, which demonstrates robustness towards variation of contextual information. We also show these results to an expert radiologist and radiographer in order to get some qualitative results. And both confirmed that the method produces detailed pancreas contouring for, they said, for every protrusion and indentation, as opposed to an approximate tracing of the organ, which is of paramount importance for an accurate analysis of the organ for making diagnosis for specific illness. The proposed approach is extended to a broader spectrum of MRI sequences and organs. You can see for each dataset 2 different medical scans with the superimposed segmentation outcome in green and the ground truth in red is proposed in this slide. In particular, I would like to note that the iliopsoas muscles, so the muscle in the abdomen, is an anatomical structure with high variability, and the kidneys dataset contain quite challenging data because it comes from a pediatric DCE MRI dataset with clinical normal and abnormal kidneys with varying level of hydronephrosis, which is a condition where kidneys show irregular size, shape, and location. And the segmentation results continue to demonstrate, anyway, statistical stability despite a high variability. Now, using our data set and apply the proposed framework, we want to compute some features, some morphological features. So we compute the volume and the curvature. The volume gives a measure of the organ dimension, while the curvature describes the organ surface and gives information about the level of smoothness and ruggedness, providing an indication about potential deformity of the organs. And this study that was carried out with the collaboration with life science school in our faculty had demonstrated what was already been observed. So that in some subjects with the type 2 diabetes, the pancreas displayed an involuted morphology with serrated borders. So as you can see, this kind of study could help also to confirm some of the previous finding. Another study that has been carried out regards feature extraction from DCE MRI volumes from kidneys. As I said before, the kidneys in a pediatric population. This work was done in collaboration with Harvard Medical Schools, and the data are from Boston Children's Hospital. So we are targeting a specific patient with some specific disease. And using the proposed approach, we segment, so using the network that I showed you before, we segment the kidneys and we identify the kidney compartments, which are the medulla and the cortex, so medulla in red, cortex in green. And the accurate segmentation of the whole internal kidney regions can be used to extract clinically important markers of renal function that could optimize clinical decision-making. An example you can see in these figures. Here, the change in grayscale intensity over time can indicate the rate at which the gadolinium contrast agent reaches the kidney, and thus gives an insight into the condition of this organ. Moreover, it might be useful to explore a large scale analysis of medulla and cortex time intensity curves against corresponding DCE MRI scans in order to develop a method that guides the clinical classification of each kidney directly from the curves, and thus help to establish the probability of, for example, urethral obstruction in a quick way and in a non-invasive way. So these were some of the studies that we carry on. But the main idea is to provide also the scientific community with a web-based framework for the automatic feature extraction and segmentation of different organs in medical scans, using the algorithms, using this AI engine that I showed you before. So we develop a framework, we import all this functionality in an application which is open source and easily accessible by the research community. It's a web application developed in Streamlit, where the main features were uploading the medical scan, visualizing different views of medical scans, process these images through the AI model in order to perform the segmentation and in order to visualize, have a 3D visualization of the organs. Then we can extract some biomarkers and we implement also some utilities features. This is a demonstration of this tool. So I hope you can see the video. We can actually load we can load the image. In this case, I'm loading an MRI of the abdominal part. You can see we have three different views: the axial, the coronal, and sagittal. And through these slides, we can change the slides that we want to see. So we can see different positions of the organs. And then in this, we can also show metadata, because medical imaging, if you undergo an MRI, you will get some DICOM file, and they hold some metadata information that can be extracted and displayed. They can hold also some patient information that obviously now has been hidden and not considered. We can here select which organ of interest we want to automatically see. In this case, I selected the liver, and you can see in each view the segmentation of this organ. Again, we can use the slide in order to change the position within the medical volume, and we can see the output. We can also get the 3D representation of the organ, ticking the box, and we can, for the time being, we can do simple thing, rotate, zoom in, zoom out, and then we can extract and save the 3D shape. And then if I go a bit further, otherwise it's too long, we can get some morphological features and download all the data that we got in a file. So the aim is to incorporate all these AI models into the development of an effective medical image analysis cloud-based application. So the aim is to make accessible this tool to clinicians, to scientists, medical care service, aiming to improve the process of diagnosis, analysis, detection of disease. So the idea is to extend this web application also with other works that we are carrying out recently. I didn't put this work in the presentation, otherwise it would be too long, but we are also working on tumors segmentation, especially for brain. And we are trying, and we are currently working on improving the visualization in order to increase the user interaction. So the objective is to use VR, AR devices for an immersive experience, and this could improve the analysis for a certain organ to have a better understanding of the current state of the health of a patient, the progression of the disease, and could also use for training purpose, for example. Also, another important thing that we are currently working on is on integrating the algorithms that I showed in a federated, decentralized system. Federated learning is instrumental in medical imaging as it allows to build a common, robust machine learning model without sharing health records, preserving the privacy. And of course, this is very important topic nowadays. In other words, federated learning allows training the model locally on user device without sharing raw data with a central server. And this preserves the user privacy and guarantees the data security. Also, it would allow to use more diverse data coming from different institutions, from different sources, different machines, increasing the number of data that we could collect, that we could not collect, but to use the number of data that could be used for the training. And as I said at the beginning of the presentation, to train the system with a large amount of data allows a more robust semantic segmentation, and we could also target different, wider data modalities. So I would like to finish the presentation speaking about the final goal of our research group, which is to build a digital twin. So a digital twin is a computed generated image of a person, usually in the form of an avatar, and this image can be used to replace a patient in a clinical setting or to help with research. The benefit of designing a digital twin in healthcare include the ability to improve patient care and research. For example, by creating an accurate replica of a patient's brain, scientists can study disease more accurately and could learn more in depth, and could also put in practice how the treatment works on human cells, seeing different modification. But how do we need, how to build, what do we need in order to build a digital twin? First of all, we need data from a large cohort of patients, as I said at the beginning. And this information can be used to train the AI models offline that work together to build the digital twin. And second, we need data from the specific patient. This information is used to personalize the model and to create the digital twin of the specific patient. It prepares the model for inference and the treatment simulation. You can see here an example using the framework that I presented so far and that we developed, extracting the information that I showed you before today. So you can see the main idea is how an avatar can carry all the previous checks that have been performed, and the doctor would be able to visualize them in an interactive way and in a collective way, making a more informed assessment, obtaining also prediction and choose the most suitable treatment plans. Additionally, by using digital twins as replacement for patients in real life, hospitals could also save money on personnels and could foster, of course, a research project. So to conclude, the concept of digital twins is currently emerging and is really revolutionized the way we approach patient care and medical research. By creating virtual replicas of individuals and their organs, we can gain a full insight into a personalized diagnostic, treatment strategies, and disease progression monitoring. And the integration of digital twin technology with the advanced AI opens new frontiers in precision medicine. We can enhance patient outcome, we can reduce healthcare cost, And as we move forward, it is essential to collaborate across different disciplines in order to invest, to develop on this and to take advantage of the potential of the digital twin in healthcare. And I would like just to conclude saying that embracing this innovative technology and considering also privacy and data security issues, we can think to a new way of providing healthcare, which is patient-centric, data-driven, and continuously evolving to meet the needs of every individual. I would like to thank, of course, University of Westminster, Harvard Medical School, and UCL that collaborate towards these projects. And with this, I conclude my speech. And if you have any question, I'm happy to reply.
Thank you very much, Doctor, for that valuable presentation and speech. I would like to take this time to apologize and highly appreciate your patience with us amidst your busy schedule.
No worries, it was great to be here.
Thank you very much. Have a good day, ma'am.
Thank you.
Moving on to the next is a session chair by Professor Nihal Kodikara, Professor IIT. Professor Kodikara received his master's and PhD in computer science from University of Manchester, UK. He has over 40 years of teaching experience at the University of Colombo. He's also an emeritus professor at University of Colombo. Over to you, Professor.
Thank you for that introduction. So we have two papers for this first technical session in computing track. First paper is developing an automated system to analyzing the software developers' interest using Twitter data. There are some authors. Authors are KNMS Nandasiri, KGLS Ananda, DVS Maduranga, KDHS Bandara, CP Vijayasirivardhana, ITS Priyatilaka. They are all from University of Moratuwa, IT faculty, undergraduates. Paper will be presented by NMS Nandasiri. Malish Sanuka Nandasiri. He's expected to graduate at the end of this year, right? Okay, his research interests are natural language processing, AI and machine learning, Internet of Things, human-computer interaction, green IT, and sustainable computing. So, Malish, you can present.
Right. Good afternoon, all of you. Thank you, Professor, for the introduction. And I'm Manish Nandasiri from Faculty of Information Technology, University of Moratuwa. I'm going to present today our conference paper. paper on behalf of our team. So our paper title is thank you. Right. Right. Okay. So, as per the overview, we will go with the introduction, why we have selected this topic, and also the problem we have faced, the solution, aim and objective, literature review, and the proposed approach, the design, implementation, and also the prepared works. So, as per the introduction, there is an underlying problem of selecting the best team of developers for a project in the IT industry. So emphasizes that the interest and preferences of developers are a crucial factor in achieving better project outcomes. So motivated and engaged developers who are genuinely interested in a project are more likely to be actively involved and deliver better results. So our research focuses on predicting their interests based on the content of their tweets. So using the proper sentimental analyzer, which is based on weighted and naive-based algorithms, we were able to accurately classify and measure the level of interest of developers based on their tweets on a given technology. So as per the problem in brief, finding the best team of engineers to work on a project is one of the biggest problems in software development. It's crucial to pick developers that are really interested in the project in addition to having the required knowledge and abilities. So the need of a system to that evaluate developers' interest levels and their passion regarding technology is essential for software development companies for team composition. So as for the solution, in order to by considering the level of interest of an IT employee, we want to discover that the best developers for a particular project in this research study. So in order to achieve this, we will use the Twitter social data media platform to get the tweets that the developers have tweets regarding the technology, and we will use the novel sentiment analyzer approach to accurately analyze their sentiment in order to rank the users. So our aim is to implement a system to evaluate the technical interest of information technology employees using Twitter data. So as per the objectives, we have built an Python client to extract the Twitter post using Twitter API, and also we have analyzed the sentiment of the extracted Twitter post to determine the technological interest level of the user, and we have determined a score for their technical interest, and based on that scores we have ranked the users, and also finally we have evaluated the developed system to benchmark it into the industry standard. So as per the literature review, we have found several papers regarding the some of them are then based on how to use the Twitter in the software engineering context, and some are about using this Twitter for sentimental analysis purposes. So in this research, the researchers have categorized the tweets into software engineering related and gadgets and technology topics, current event of the technical topics, and daily data by considering three communities which are Eclipse, Linux, and MX units. In these researches, they have found some subcategories within these communities which are problem solving, self-promotion, complaints, and a use of a specific tool for work. So we have presented the percentages that the tweets they have posted regarding these subcategories. So as per the another research, the sentiment and topic classification of messages on Twitter. This strategy have used natural language processing to classify messages posted on a Twitter based on a sentiment and topic of the tweets. So they have used a natural language toolkit for NLP tasks and Python Twitter tools. Then they have used naive-based classifier for the classification tasks. So when categorizing the Twitter contents for sentimental, the accuracies was 29.9 and 33.5, which is the author himself had described it is not better than a random choice. So in this research, the program's performance is constrained by the trained naive multinomial based classifier poor classification accuracy. So they have suggested few techniques to improve the accuracy, such as increasing the size of the training data set. And as per another research, sentiment analysis on Twitter data, the authors has first described the importance and challenges in analyzing Twitter sentiment on social media platforms. They have presented various approaches and techniques for sentiment analysis on Twitter data, including lexicon-based approaches, machine learning approaches, and deep learning approaches. So as per the limitation and future direction, they have needed a more robust method for handling sarcasm and irony. So as per the research gaps we found by these researchers, these previous works have on analyzing Twitter posts focused on identifying categories related to a post tweeted in a software engineering group, but not on the interest levels of the developers has on that technologies. So as for another research gap, the researchers that analyze the interest level of the post has mostly conducted regarding review of a product, but not on a post related to a software engineering topics. So most of the interest level analysis were designed to analyze the general tweet content, but not regarding the tweets in a specific area. So our focus here is to build an interest level classifier which could provide more accuracy in a specific content of tweets regarding a technology. So as per our approach, we will use this system to extract tweets from users on Twitter platform, and then we will pre-process the tweet content. Then we will perform a sentiment analysis to provide the interest score for a given technology. Then we will use that interest score to rank the users. To accomplish this goal, we have to pass several stages. So this is the high-level architecture of our system. So this will take training data set from the Twitter database, and also it will extract developer Twitter post from the Twitter database. For this system, we need to input Twitter username and also a technical keyword. Based on the username and the keyword, the system will extract the developer's Twitter post, and the sentiment analyzer will get training data set from the Twitter database. So it will use this sentiment analyzer, which is based on a weighted and naive-based algorithms to calculate the interest level of the user. So we will generate an interest level score based on that technology for a user. So that score will be finally used to categorize, to rank these users. So as per the analysis and design, the tweets are extracted using Twitter API platform from a tailored tweet to a user account, and a Python IT client is constructed in order to access the API and pull tweets and other information from it. Prior to being inserted into the main processing flow, the raw data must be undergo pre-processing. So the actions listed below are considered for the text preparation steps. So these actions are tokenizing, stemming, filtering, and weighting. So naive-based classification is used as the classification theory, and it is a classification algorithm that uses to use Bayes' theorem in its applications. Naive-Bayes variant called multinomial naive-Bayes was created in order to address the classification of text content. So we have used the multinomial determination is used the multinomial naive Bayes as a classification characteristic together with the words weight frequency. Here is the Bayes theorem formula. So as per the implementation, for the data capturing part, the Twitter API is used to access Twitter data and extract Twitter posts. So we can further extract the Twitter posts based on the Twitter user and the keywords used in the tweets by applying search queries when extracting data using the Twitter API. So here I have insert the sample code that we have used to extract Twitter post. So in the sentiment analyzing process, in this model we are proposing a sentiment analyzer to analyze the sentimental value of the Twitter post regarding a technology. The sentiment analysis is based on Vader and naive-based classification algorithms. So our goal is to achieve a higher accuracy when analyzing sentiment value on the post related to a specific technology. So the inputs are going to be the username and the technological keywords. It will extract the user's Twitter post from the Twitter database, and the Twitter database regarding the technological keyword will be extracted again to use as the training set for our algorithm. So using those posts, we will use this will go under various sentiment analysis in order to have sentiment analysis. Then it will insert as a training data set for naive-based sentiment analyzer in order to have more accuracy regarding the user's Twitter post regarding the technology. So the interest level of the user will be produced as the output of our system. So this is a sample testing sample input in our code. So the custom state was I love learning Node.js. The predictions were it has a positive prediction of 0.84, which overall identified as this statement is to be positive. So to compare the accuracy of the proposed sentiment analyzer, accuracies will be taken from a direct approach using the weighted sentiment algorithm, and also a direct approach using sentiment analysis based on a naive-based algorithm. So the comparison will be carried out using a Twitter post of datasets which consists of technology-related posts. According to this comparison, the proposed system effectiveness is being tested. So as for the results, the effectiveness of the proposed system is tested by the accuracy of the proposed sentiment analysis with weighted sentiment approach and also the naive-based sentiment approach. So for the data set, we have used sentiment 140 data sets, which consist of 1.6 million tweets, so to extract software development technology related tweets for the testing accuracy. So the following table indicates the accuracies of each approach in predicting sentiment for each technology based on the given number of tweets. For the Java script, we were able to extract 91 tweets. In the Veda approach, it has calculated that the 63.04% accuracy was produced. For the naive Bayes, it was 50%. For the proposed approach, it was 59.78%. So in this Java script related database, the proposed approach has scored less than the Veda approach. Later we have found that it is because of the data set was more biased as the training data source for naive-based approach and the proposed approach has been biased. These scores has been less than the Veda approach, as later was an unsupervised algorithm. So MySQL and ASP.NET, we have used 96 tweets for MySQL to MySQL database. The Veda approach has calculated 59.37% accuracy, and also naive-based approach has 56.25 accuracy, and the proposed approach has been calculated as 67.71 accuracy. So ASP.NET also there were 41 tweets. So in the weighted approach, it was 51.21%, and also naive approach, it was 52.54%. The proposed approach has scored 56.09%. So although in the JavaScript context, it has score less than the weighted average. Overall, we have able to generate a high accuracy for the sentiment prediction across all the technologies using the proposed approach. So while the weighted approach and naive-based approach have varying level of performance, the proposed approach performs better than other two approaches in terms of predicting sentiment for a given technological tweets as per the accuracy for the about technology-related data sets. So these are some screenshots of the moment that we have calculated the accuracies. This is for the JavaScript data for weighted and naive-based approach, and also this is for the proposed sentiment analyzer for the JavaScript database. In here we have MySQL database, and also here we have ASP.NET data set. We have tested the accuracies for that data set. So as the final output, we have given the interest score for the users. Then according to that score, the users will be ranked. In here we have a positive and also negative scores, which means in the negative, it means that the users have a negative interest toward the technology by post they have tweeted, and also in the positive score represent that the user has a more positive interest regarding this technology. And also we have given the 0 as the user hasn't posted anything regarding this technology. We have considered he has a 0 interest, which is neither negative nor a positive. So as per the conclusion, this module emphasizes that the interest and preference of the developers are crucial factors in achieving better project outcomes. So using the proper sentiment analysis, we were able to accurately classify and measure the level of the interest of the developer based on their tweets with an overall higher accuracy than the compared existing approaches. So our study also compared with the orient body of literature on how to use social media data for understanding the activities and interests of developers. So while previous studies has focused on categorizing the tweets into different topics or analyzing the online behavior of the developers, our approach focuses on predicting their interest level based on the content of their tweets. So as per the feature limitations, one of the challenges we have to face is that when gathering enough data for regarding a given technology, some development technologies might not be popular among the developers as the rest. So and also the change of policies regarding the Twitter API was an issue as we had to face, as it provided some new restriction when extracting tweets using the Twitter APIs. So as per the future works, in this research study, we have only found some negative and also positive interest levels, but there can be a neutral interest level also. And also in this research, we have focused on finding the interest regarding technology, and this with slight modification, with some modifications, we can use the interest analysis also to find the interest in other areas as well. So, thank you. Because they have posted tweets that saying that they have some dislikes regarding the technology, so they will have a negative score.
0 means they are not interested.
They are not interested.
Okay, thank you very much.
Thank you.
train the database?
Yeah, to train the database, I have used the dataset extracted from the Twitter itself. So,
Is that really belongs to the developer's data?
yeah, because we have used the technology keywords when we figured out in the dataset to train the dataset. So it will only take that if we enter MySQL, it will only take the.
No, my question is others also, students and others can use the MySQL and the JavaScript as well as .NET environment. So then how do you really say that this is for the developer's data set?
So when extracting the training set, we have not considered that it's belong to a developer himself. So only in ranking that user, we will take the username for extracting the data for that user. For in the training data set, we have no restriction like that. This is belong to a developer or a student. So the persons may posted regarding that technology, maybe a student who's having a technology interest about that tweet.
Regarding the sentiments, do you consider the negative sentiments as well when?
Yeah. So in this research, we have focused that the sentiment level has positive and negative. So in here, if the person has posted about some positive things regarding the technology, they will have a positive score. If the person has posted tweets regarding some negative feedback, he will have a negative interest as the score.
Right, but that person might be knowledgeable about the technology.
Yeah. In here, I have considered about the interest, not about the expertise level.
Right, and so in from the original Twitter data set, when you kind of filter out the programming related or technology related tweets, as I understood, you have considered certain keywords, right?
Yeah.
So would there be a better approach, like rather than doing that, would it have been better to use some kind of text classification, because when you go by keywords, there can be false positives and so on. What do you think?
Yeah, as for the future approaches, we have considered that when you extract in the tweets, we have trying to classify the text belong to that technology as well without getting that data directly from using a keyword.
And because we feel that maybe some kind of text classification would have been better when you look at the entire tweet and make that.
So actually this must be expanded because most of the nowadays most of the developers are using frameworks and the web-based applications like Oracle like and also. So this is not to indicate such type of technologies. So you have to reconsider it.
Yeah. So there is also a limitation we have to face because some technologies might not be popular among a larger group of people. So in order to we have to address that in the future.
Okay, thank you.
Thank you very much.
So our next presentation is predicting the possibility of chronic pancreatitis by Bhavanta Vikramarachi and Iresh Bandwala. Both are from IIT, Informatics, Institute of Technology. So will be presented by Bhavanta Vikramarachi. He's a software engineer at present, and his research interests are deep learning, artificial intelligence, and cyber security. So Bhavanta can present.
closed and restarted applications. Yeah, no, they will display that. Okay, no, okay. Yeah, sure. Hi, good afternoon, everyone. So, my name is Banju Kumarache, and my project idea was to predict the possibility of chronic pancreatitis. So, throughout this lecture slides, first I will explain my problem domain. So, this is a cross-domain project. So, there's a bit of medical domain touch in the project itself. So, I have first give a brief idea of what chronic pancreatitis is, and then I'll explain what the methodology that I follows during this project to get the prediction, and finally I will present limitations and future enhancements for this project. Alright, so the project background is first I will explain what's pancreatitis. It is an organ located in the abdominal cavity behind the stomach in front of the spine. And when it comes to pancreatitis, there are mainly two purposes, functionalities, and exocrine and endocrine. And when it comes to exocrine functionality, it's responsible for digestion of secretion enzymes like amylase and lipase. When it comes to endocrine functionality, it releases hormones that regulate blood sugar and insulin and some enzymes like insulin and glycogen. So when it comes to pancreatitis, it happens because of the inflammation of pancreas. There are mainly two types of pancreatitis as acute and chronic. Acute means the short-term pancreatitis, which means the pain goes for shorter period of time and then it will go away. But when it comes to chronic pancreatitis, the severe pain keep happening over and over again, and finally it will result in pancreatic cancer. So there are several factors that happens to inflammation of pancreas. So mainly they are gallstone and heavy liver consumption are the primary two factors. Other than that, there are genetic and injuries and infection can cause the pancreas inflammation as well. So when it comes to inflammation, it simply means that the pancreas cells starts to die and the functionality of the pancreas will lose with the time. So in this picture you can see the gallstone pancreatitis, which happens because of calcified stone getting blocked the path of pancreas enzyme secretion path. So mainly the calcified stones form in the gallbladder get stuck in the pancreas path, and as a result the enzymes secrete from the pancreas itself get stuck in the path itself and start self-digestion. Because of this inflammation, pancreas occur by causing the dying of its own cells. Well, when it comes to symptoms, there are mainly 4 symptoms as abdominal pain, vomiting, false smell, stool, and weight loss. Here, when it comes to pancreatitis, especially chronic pancreatitis, there are a few diagnostic challenges because this disease don't have any specific symptoms, and there are some overlapping symptoms with other diseases. And to detect this, the diagnostic procedure is a little bit longer than the normal disease diagnostic procedure. So here when it comes to no specific symptoms, the main issue is all the symptoms present in the chronic pancreatitis will be shown in diseases like as gastritis, hernia, likewise. The early detection of this disease is very important because the damage of the pancreatitis is irreversible, and there's no treatment for this pancreatitis. Because once the damage is caused, we can't reverse the damage. The only thing we can do is to comfort the patient's living. And also this is a severe pain disease which causes huge abdominal pain for the victim of it. And if this keeps happening over and over and over again, it may end up in pancreatic cancer, which is one of the most deadliest cancers. Plus, it may cause diabetes. So when it comes to research gaps identified, for the moment there's no any computer-based research carried out early identification of this chronic pancreatitis disease. Most of the times they focused on acute pancreatitis identification. And when it comes to those multi-disease prediction systems, we can't use those systems when it comes to this disease, because this disease didn't represent any specific symptoms. And also when it comes to abdominal data sets, especially abdominal medical data sets, there are a lot of data set limitations. There are very few data sets available in public in order to give us a prediction or develop a model. So in this project, my main aim is to early predict the possibility of chronic pancreatitis when MRI or CT scan or both images are provided, which again doctors diagnose the disease in a very recent. So normally when it comes to traditional medical body data, it will take some time for doctors to diagnose this disease. By the time it may cause a lot of damage to the patient's pancreas. So here I have added my 3D architecture of the system. Basically, the prototype allows users to select CT or medical image and then insert the image. And I have developed two superior models to MRI and CT detection. So once user inserted their MRI and CT, the prediction will be taken considered by each model and then output to the user to the detected percentage. And when it comes to model, there are two models, as I mentioned, CT and MRI models. For each model, I have used same CNN architecture, but separate hyperparameter tuning was done for each model. When it comes to layer design of this model, there are 8 convolutional 2D layers I have used for the feature extraction purposes. And for batch normalization, layers have used to normalize the activation. And they are also following up with 8 Likerelu to introduce nonlinearity, and 2 max-folding 2D layers to reduce the spatial dimensions, and 3 dropout layers to prevent overfitting, and 1 flatten layer to flatten the multidimensional feature maps to 1D, and 2 dense layers to classification tasks, and 1 activation layer to obtain the desired output of the possibility. So when it comes to high-level overview, as explained, the UI itself allows users to insert the image, and then from the backend side of the side, we pre-process the given image, and the output will be displayed to the user. When it comes to testing of this model, we have used hyperparameter tuning, and we have checked that the performance along with separate performance metrics like accuracy, F1 score, recall, or precision. And then of course functional testing was done, and non-functional testing was also carried out. The qualitative evaluation was done by a domain expert and technical experts, and the quantitative expression also done for functional and non-functional requirements. Here I have presented the accuracy, F1 score, recall, and precision values that I have gained during the hyperparameter tuning process for each dataset. Here, as you can see, with the increase of batch size, we can see some overfitting scenarios with the values that happens for the accuracy and F1 score. And here I have presented the scenario for both MRI and CT. And here also I have done the test evaluation through several eWatch counts to find out the best accuracy and along with the F1 score, recall, and precision values suitable for each model. And also next slide, I will show the separate learning rates that we can obtain the best value for CTs and MRIs. When it comes to finalized values, I have used EPOS as the 6, batch size as 16, and learning rate as 0.7. Here also one more thing, when it comes to CET data sets, there are a few images that we have for the abdominal MRIs. We don't have much of abdominal MRIs comparative to CT images, so the EPOS count is little bit increased in compared to CT images. Other batch size and learning rates are values similar as CT images. So when it comes to our final model, we were able to take the output of accuracy of 89.55 for the CT model and 18.19 for the MRI model. Here, when it comes to limitation, the main limitation is dataset limitation. There are very few datasets available, and there are also to train these models, lot of GPU resources needs to have, so it will take a bit of time as well. So GPU resources is also one of the limitations that I have to overcome during the process. Well, when it comes to future enhancement, I would suggest to train the model with more MRI or CT images to get the maximum accuracy, or to develop an AC GAN model which discriminates itself, can differentiate the pancreatitis or healthy MRI or CT images. When it comes to contribution of body of knowledge, the main contribution of this project is to detect the pancreatic inflammation. So the CNN architecture that I developed have the ability to detect that and then differentiate the possibility of pancreatitis against the healthy possibility. Then also, other than the prediction results, I have displayed detected possibilities in the application itself as well. This helps to reduce the misdiagnosis rates. Here, when it comes to CNN approach, in terms of technical contribution, I have used CNN binary classification and also focused on MRIs as well. So all the other researchers carried out in this domain primarily focus on CT images. And also I have compared different performance metrics to evaluate my model. So with that said, that's it for my end. I would be happy to answer if there's any questions.
So,
yeah, there's a public dataset available. There's one dataset which has these healthy images plus pancreatitis images.
so here you are basically the problem domain is on predicting.
Yeah.
Yeah. And at what intervals, like, is there some sort of timeline in terms of prediction? Now, you have used a data set to train, and this data set has I mean, it's a common data set, and but you it's a common medical data set, but you have extracted pancreatitis the timeline, like the observations.
Well, there are two data sets, like one with healthy images and another one is the pancreatitis images. So what I did was...
Yeah, I was looking at the, you have said there are 3 models, no?
No, 2 models.
You have used that as well, right?
2 models.
Okay, anyway, in your paper it says MMIC3 clinical database.
No, that's not the same.
Okay.
That may be a literature review one.
Yeah, so thanks for the nice presentation. Now the CT image-based model and the MRI image-based model, do you consider them separately, or are they combined as an ensemble? Or
They have been considered separately. I
Right.
have trained them separately, and there are two separate models to give the prediction.
so, do you think it's better to aggregate those predictions in some ensemble model, like combined model?
Well, not for now, but in future, I would like something like when we develop an AC GAN model, since we can have different classes. So I would say it would be helpful if we can aggregate both data sets.
I have one question.
Yeah.
Then from the MRI and CT scans, the doctors can diagnose what this patient has. Then from your model, rather than predicting, you can verify the doctor's diagnosis, ne?
Yeah, that's right.
So
So
then,
in some cases, like when it comes to gallstone pancreatitis, we can clearly visible they mean MRIs or CTs, but when it comes to something alcoholic-based pancreatitis, we don't see any visible SARS. So that's when my model comes to play. It can give the prediction. So when it comes like in traditional method, what doctors doing is, if they sense this is a pancreatitis disease, there's another technique called ERCP. So that's they made the final decision whether the patient consists of pancreatitis or not. So, but it's not something they did doing at the first place. It's something they do at the later stage. So with my model, it sort of increased the diagnostic procedure time.
Thank you very much.
Thank you.
Hi everyone, I'll just stand here because that's not going to help me. Right, we are moving on to the token of appreciation session now. I would like to invite Mr. Sunil Bandarawatha, CA for Informatics, to present the token of appreciation to Professor Nihal Kodikar. Thank you. Before we take our lunch break, I would like to introduce the judge panel of the computing track. We have Professor Lasit Gunawardana, Dr. Darshana Kasturi Ratna, and Dr. Rohan Samarsingh. We will be having 1 hour of lunch break that will be starting around 1:50. And in the meantime, after the lunch break, we will have the poster presentations in the main hall. However, we have to be back after the lunch break here that I will announce after the time confirmation for the technical session 2. Thank you.